Assalamualaikum and good day everyone. My name is Anwazir Ahmad Shahimi. Today our group from Group 1 will be presenting the digital audio filtering system assignments using my lab. So a little bit of the background and theory of audio filtering. So in a real world, signals like a recorded human voice rarely exist in a vacuum. They are almost always corrupted by unwanted signals which we collectively call noise. So the human voice, vast majority of acoustic energy and intelligibility in human speech is concentrated in a relatively narrow band, typically between 300 Hz to 3400 Hz. And then the noise generally falls into two categories. The first one is the broadband noise. It is like a hiss or rumble that spreads across all the frequencies, while the second one is the narrowband noise, a specific steady hum or whistles. So digital filtering is the mathematical process of modifying an input signal's frequency content to enhance the desirable parts of the signals, usually the voice, while suppressing the undesirable parts, which is the noise. So if we take a look at the corrupted audio signals given, we can clearly detect which one is the voice, which one is the noise. The voice is obviously the 0125, and then the noise is the humming and the beeping noise in the background. So our objective is to filter out the noise by applying the signals filtering concepts. So next, first and foremost, we have to extract the audio file. So first we have to insert the audio inside the codes, which will be using the UI get file function. And then we have to check whether the audio is in mono or stereo. Because if the audio is stereo, we have to convert to mono, since the stereo audio require doubles the computation time. So after converting, we can use the min function to allow us to obtain the straightforward mathematical array of audio sample, which we call SN, which we will be using to plot Tusky later. And then after we successfully extracted the audio file, now we can analyze the raw noisy audio. So looking at the time domain plot on the top, you can see the audio wave is fuzzy and chaotic. So the noise and the voice are completely meshed together. So we can't really see what's going on. So we cannot fix it. So we use the fast Fourier transform to look at the frequency spectrum on the bottom. So here the problem becomes much more obvious. There's a massive spike of noise around the 800 Hz mark, and a lot of unnecessary high frequency noise outside the range of normal human speech, which is around 200 to 1500 Hz. So to clean this, we designed a unified system by cascading two Butterworth IR filters. First, a bandpass filter from 200 to 1500 Hz to act as a window, keeping the intelligible parts of the voice while throwing away useless rumble and hiss. Second is a band stop filter from 750 to 850 Hz to surgically delete the loud 800 spike we saw earlier. And as you can see on this graph, we tested different filter order. We rejected the second order filter, which is the red one, because the slope is too lazy and leave too much noise behind. And then we also rejected the sixth order filter, which is the green one, because while it is a steep, which is practically what we wanted, but a high order IR filter introduced audio distortion and risk crashing the system. So we chose the fourth order, which is the blue one, because it is the perfect sweet spot, as it cuts the noise aggressively without warping the audio or tightening the system stability.
So we will be going to part D, which is frequency response plot of filter. So for the first top graph, it is a combined linear magnitude graph. It basically shows the filter volume control on the scale from 0 to 1. This linear plot shows us that visually our converge design works perfectly. Based on the graph, we can see the flat top area between 200 Hz until 1500 Hz. Means our human voice frequencies are multiplied by 1, but at the 800 Hz, there is a sharp drop to 0, means our band stop filter is successful to remove the frequency noise. Then for the middle graph, it is a magnitude response in decibel. So based on audio engineering, a drop of 6% dB makes the volume cut into half. So based on our graph, at 800 Hz, the tone down is past negative 40 dB. This means hiss and whistling sound are reduced to less than 1% of its original sounds. So it makes the sound can't be heard. So for the bottom one, it is a phase response, which function is to track how much the filter delays. Because of choosing IIR filter, the phase is non-linear, meaning that different frequency delay by slightly different micro of second, while the non-linear can be distorted by digital data signals. And as human ear is naturally insensitive to minor phase variation in speech, so it doesn't affect much for the benefit that we can get to using the IIR filter. Next, this is our resulting filter impulse response. This graph shows us two crucial things, which is the first one, based on the graph, the dot ring out over time rather than shutting off instantly. It demonstrates the infinite impulse response, which is nature of the IIR filter, and that also means the math relies on the feedback loops. Then the second one, because the oscillation rapidly decay and shrink down to 0, it visually confirms that our system is highly stable and won't suffer from infinite mathematical runaway. This slide is showing pole 0 plot of HZ. As you can see on the graph, the blue circle are the zeros and the orange crosses are the poles, while the red dash circle is the unit circle. So the condition for discrete time system to be stable, all poles must be inside the unit circle where Z is less than 1. So since all the poles are inside the unit circle in this plot, we can conclude that the system is stable.
Now, I present the results of our digital audio filtering system. The slide shows that the output signal after filtering. If we compare the waveform before and after filtering, we can see that the filtered signal is much smoother. The avoided high frequency noise has been greatly reduced, while the main speech waveform is still preserved. This shows that the filter improved the audio quality without significantly affecting the original speech. So next, we evaluate the filter's performance in the frequency domain using the FFT. Compared to the original spectrum, the background noise outside the speech frequency range of 200 to 1500 Hz has been significantly suppressed. So we can also see that the large interference peak at 800 Hz has been removed by the bandstop filter. So this comparison confirms that our filter successfully removes the unwanted noise while preserving the original speech.
0125.
Based on both the time domain and frequency domain results,
0125.
the filtered audio is much cleaner than the original recording.
0125.
The background noise has been reduced, the 800 interference
0125.
has been eliminated, and the speech remains clear and
0125.
understandable. In conclusion, our digital audio filtering system successfully achieved the objective of this assignment. By combining a Butterworth bandpass filter with a bandstop filter, we were able to remove unwanted noise while maintaining the quality of the speech signal. That's all, thank you.